Hello, we are Team ME35, and our senior design project is sample acquisition from hypothesized surfaces. So to give some context, NASA already sent a probe to 16 Psyche, and it's just going to orbit the asteroid. It's going to confirm our hypothesis that it is a metal-rich asteroid, which, if true, would be interesting to send a probe to actually sample the surface, which is what our design is going to help accomplish.
So for the objectives of this project, the device has to be able to extract samples from the surface of Psyche. It needs to fit within the constraints of a typical rover. It needs to be able to withstand its operating environment, which would be the surface of Psyche. It needs to survive the journey to its operating environment, so be able to take off from Earth's surface. And it needs to stay within the budget of similar NASA sample acquisition projects.
So here's an overview of the full design of the sample acquisition system. On the left you can see the coring system, which consists of the arm and drill, and on the right is the storage system, which is a tray-like mechanism that holds all of our sampling tubes. On the right you can see how the system operates, wherein the coring system picks up a drill bit, moves it into position, and then slowly moves the drill downward while the drill actuates to core the sample. Then it places the sample back into the storage system and is ready to pick up a new sample tube to core another sample.
So for the drill system itself, the main drill is an ultrasonic piezoelectrically actuated drill. This drill operates at incredibly high frequencies, which allows for a very low preload to be applied to the drill to drill into the surface. The drill bits themselves, they're single-use coring bits with a slope inside of them, which shear off samples, securing the sample inside the drill bit, seconding using it as a storage. The bits are magnetically attached to the piezoelectric drill using the magnet as shown in purple there. That is how they're attaching and detaching from the drill and going into the storage system. And the drill finally is attached to the robotic arm via a proprietary design as seen in yellow.
So looking at the storage system, it's a fully enclosed box that allows the samples to be held in place while also being protected from outside contaminants. This is achieved through grommets, which seal with the bottom of the sample and provide a sealing force that holds the sample tube in place and prevents dirt from getting in or out. A top grommet protects the inside of the box when a sample tube is removed by having flaps that cover up the hole. There's also side panels which provide an overall level of dust protection. Here's an overview of the Bolt FEA results, showing all the stresses from launch, and none of them exceed the yield stresses, and if you want to look at more details, feel free to pause the video.
And so for the drill itself, since it operates at such a high frequency, we needed to determine fatigue. With FEA, we've determined the equivalent alternating stresses on the drill and the arm, and all the numbers prove that fatigue will not be an issue. So here are references, and thank you so much for watching our video. We look forward to seeing you at the 2026 Phase of Meyer Conference.